Hello, everyone. Welcome to the reveal of our new AI Factor product. We're very excited to finally put it in your hands and see what you think. My name is Marco Salerno. I'm the founder of Portfolio123. I'm joined today by Ricardo Tambara, our analyst, Dan Perrette, our QA engineer, and Claudio Capetta, our data scientist. Before we start, a big thanks to all of you for giving us invaluable feedback, suggestions, and inspiration throughout the years. So yeah, big thanks for your support. It makes a huge difference. Yeah. Some Zoom settings you may not be aware of. If you want to raise your hand during Q&A, click on reactions in the Zoom toolbar. You can hide participants so you can get a better, bigger screen by clicking on the right corner, hide non-video participants. So the design goals for AI Factor, obviously intuitive and very little prior AI and data science expertise. That was our goal. We didn't have any expertise, so that was a good goal. Sensible defaults throughout, so to help you not get hurt, avoid pitfalls, curve fitting, outliers, NAs. We think it's a pretty full-featured ML product. We covered the main areas of a machine learning workflow. Of course, there's going to be a lot more coming after this launch. And it's a complete integration. The AI factors can be used like any other formula throughout the system, in rules, ranking systems, screens, etc. It just becomes a regular formula to access the prediction. We strive to make it affordable, and for what it is, we think a well-engineered, cutting-edge product. You only pay for what you use, but for you guys, the beta users, there is absolutely zero cost. So for this presentation, I'll move quickly, as most of you are familiar with AI concepts. Feel free to use the chat during the presentation, and after we'll have the Q&A. And of course, the recording will be available after the meeting. So to access AI factors, it's enabled right now for all the beta users. You will see it in the research menu right here. And I'll start an AI factor from scratch, just to give you an idea on how to start one. And then I'll switch to one that I've been working on. So the first thing you have to do is decide what you are trying to predict. We have created many pre-built targets. It's a slightly different formula than you're used to, because it has to evaluate in the future. So, for example, for performance, for predicting performance, you have specialized functions like future relative percent change. For other things, you have to be a little bit more creative. For example, if you're trying to predict the sales growth, you have to use FHIST with a negative offset. So it gets a little tricky, but hopefully this pre-built targets will kind of show you how to do it. If not, of course, ask us, and you can create your own, absolutely. I'll just pick a pre-built one, 3-month relative percent return. Of course, you have to pick your training universe, your benchmark. And you have to give this AI factor a name, and it should be a name that reflects what you're doing. So you can just copy the target. Obviously, I have a few already. So this is version 9. In this page, you will find some filters that, again, hopefully protect you against outliers that can skew the results. You may be used to these by now because we have them in other places. For example, if some stocks are below $10,000 per day liquidity, they will be excluded from the training and so forth. Obviously, with S&P 500, it's not going to be a problem, but for small caps, this additional rules make a big difference. You then have to set a preprocessor. Everything has to be normalized for AI, for machine learning algorithms to work better. At the moment, we only support a single preprocessor for target and features. We're discussing potentially supporting multiple versions of the preprocessor. The defaults are pretty good. Z-score, normalize on the entire scope of the data set, and some sensible trims and outlier limits. Then you have to decide the data set that you're going to use for validation and training. You need a period. So let's do 20 years. And here you can, and the frequency, every 4 weeks, we're going to suck in the data and create this data set for the machine learning algorithms. Again, some protection here against outliers. If a stock returns more than 200% in a 4-week period, it will be capped at 200. If you notice over here, your data set stops around March because your target look ahead is 13 weeks. So this data cannot be used because there's no target. There's no future value. Here is where you define your features. So this is similar to creating a ranking system, except you don't have to specify, the direction of your sort. The algorithms will do that for you. We have created a whole new set of predefined factors. They're a big improvement to what we have right now in the reference, and this is going to be made available in all the other parts of the website. It's some of them are just straight factors, but organized and easier to access, grouped better. Some of them are just, just a factor, but some of them are formulas. If I can just find one. Okay, much easier to use. So for this AI factor, I don't know which one to pick. You can just add them in bulk. I just added 27 factors. Here we go. So the next thing you should be doing is analyzing the features. We try to obviously create features that are problem-free, that have good distributions, etc. But if you find something that, especially for Z-score, if some of the distribution don't look right, you can, for maybe this one, you can edit the formula and perhaps add a log transformation. So, okay, so that these are the features that you're going to use for training. You then next have to load the data set to our AI backend, which runs in Python. So it's a completely separate system. Once you start loading the data set, though, you can no longer make any changes to this AI factor. Obviously, everything has to be consistent. and it gets, in essence, locked down. If you want to try different data sets, you have to start a new AI factor, a new version. You can choose to calculate target information regression, but it's kind of it can be time consuming, maybe 5-10 minutes. And you only need to see it at the beginning. So we can just disable it for this demo. And while this loads, you can start planning your validation. So the goal here is you're trying to find a model that works well with your features and your universe. So what is a model? We have some definitions here to help you. Model is just a machine learning algorithm like XGBoost and associated hyperparameters. So you can have infinite models to help you. But to validate which model works best, you have to decide how you're going to validate this. We have created 4 basic standard validation methods: time series, cross-validation, rolling time series. So you should be familiar to this setup. It defaults to 4 folds. You can specify the training period for each fold, and everything else gets calculated automatically. So, for example, if you want to train for 6 years, everything adjusts so that you get the most out of your data set. What's going to happen is you're going to train 4 models for each model that you add, and it's going to train during the green period, the training period. Then there's a gap that you can change to avoid leakage of data. You can make it 0 if you want. You can make it 2 years, and then during the holdout period, it will do predictions, and then it's going to grab these predictions, and with those predictions, it's going to create portfolios based on deciles or whatever quantiles you choose, and that's going to be your validation output. Then it moves on to the next fold, does the same thing. So what you end up here is 4 outputs, and they're concatenated together to create a seamless single portfolio. Obviously, with this type of validation method, you can only do a backtest of about a little bit over 10 years. You can also reserve some data for testing. This data will be completely unseen by the validation, and it can be used as a final test of the models that you picked. So let's add some models. So this is the tricky part where a lot of data science experience is required if you're going to create your own models. So what we did is we created many predefined ones. And I'll just add a few so you can get a sense of how it works. We'll be adding more we'll be adding more, of course. Oh, somebody's on the waiting room, sorry. Okay. But for now, we have, you can see the difference between them. Extra trees 1 is meant to be the fastest one. So, 100 estimators, etc. Extra trees 2 has more estimators. So it takes longer to run the higher the version. And you can, of course, create your own, and you will have to understand or hyperparameters. We have some links here for XGBoost, for example. And so when you edit this, when you create your own, you can just start off from extra trees 1. And we only show you the hyperparameters that we chose to modify from the default. If it's not here, you can just add it and off you go. So once the data set loads, which it has, you can begin validation. You can simply select them all, click validate. And here you have to choose what machine are you going to use to do the training and the validation. We have set up different size machines. And what matters here is the type of algorithm that you're using and the type of hyperparameters. There are some algorithms that are multi-threaded, which will benefit from more CPUs. There's also one of them requires a lot of memory. This is a hint. We don't know if it's going to require a lot of memory because it's based on a lot of things. But these tags should help you decide what type of worker you're going to use. And then we have different kinds, as I mentioned. There's a special purpose high memory one that has 178 gigabytes. And the others are just combinations of CPUs and RAM. This is a cost that we're thinking of using per hour. Of course, none of this matters during the beta testing, but you'll get an idea of the cost because we're going to keep track. In fact, you can see it today. I spent 18 cents. Okay. Yeah, and then you can decide which you're going to get the worker based on this setting, whether you want the most expensive that is available or the least expensive. And yeah, I mean, obviously, if your algorithm benefits from CPUs, choosing a more expensive worker versus a cheaper worker, it's going to probably be the same. If it doesn't benefit from extra CPUs, you don't want to choose a worker that has CPUs that won't get used. So you click start. They get submitted to the AI backend. And yeah, it starts. Well, so let me switch to a AI factor that I have built before. This was just a test. To show you some, more sensible results. This is the S&P 500 AI factor. And all I did is I just did a 20-year data set. I threw the kitchen sink at it, 321 features. These are all the pre-built features that I showed you before. Something interesting in the data set pages that I didn't show you before is the statistics. You should take a look at this to see if your data set has, for example, too many NAs. This column shows you the percentage of NAs in the data set. Obviously, with S&P 500, it should be pretty clean, but something like tangible book still shows about 29% of the data points as NA, but probably, I think 29%, 30% should probably be your high watermark, and perhaps decide to throw it out if it exceeds that. And here you can also see the target information regression is just some regression against the target, is completely model agnostic. And you may potentially use this. It's a relative, it's relative data, right? So the size of the bar doesn't really matter. What matters is the relative value versus the others. So you could perhaps choose to eliminate the worst ones to see if it improves your results. And yeah, for this AI factor, I chose K-fold blocked, 4 folds. I added several models. Some are neural nets, some are your standard machine learning algorithms. And these are the results. So in the results, you have to decide first how you're going to group your predictions. I chose 25 quantiles. So since this is the S&P 500, it's basically creating portfolios of 20 stocks each. And then we have a table that you can rank all the different models. And you can choose what's important to you. If I chose root mean squared error as one of the statistics that I like to see as low as possible, right here. I call this statistics the data science statistics, right? And then all these are portfolio statistics. What is happening here is that the high is the top bucket portfolio, and the low is the lowest bucket portfolio. If you're interested in long short, you may choose some of the statistics for high minus low. If you're mostly interested in going long, perhaps you just care about average annual return, higher Sharpe ratio, lower standard deviation, and all your models get sorted based on the combination of all these statistics. What's interesting to see is the model that took the longest ended up being the best. Actually, I didn't show you this. In the validation, if you sort by this column, you can see how long it took for each validation. SVM3 is particularly slow. So that's why and it's single threaded. So that's why we added these tags to let you know that you're gonna wait a while. And if your universe is bigger than S&P 500, you might wait a couple of days. I thought it was just something wrong with the hyperparameters, that it was not converging, but it ended up being the best. So I don't know. So let's take a look at the actual results for SVM3. And the first result is a lift chart, which just measures the accuracy of the predictions versus the actual. So predictions are all the predictions that it did during the validation period. So it's a nice normal distribution. They're grouped into 100 quantiles. And then what we show you here is the average that the average actual. So what you want to see is the red line sort of follow the shape of the predictions. As you can see, there's definitely a nice relationship. It's not super pronounced, but again, this is the S&P 500. It's very hard to beat the S&P 500. Just a little bit makes a big difference. So that's what the lift chart is for. We have some small caps AI factors where this red line is almost identical to the blue line. And the performance also is amazing. Other things you can do to analyze the models is you can look at the portfolio. So again, here is these are portfolios, these are quantiles, 25 quantiles, and we display the top quantile and the low quantile. There's a nice separation here between the high and the low. The other thing I look at is a nice consistent excess return throughout the 20 years. This is something that we have almost never seen with our classic ranking systems. Either all the performance comes in the first 10 years or the second 10 years, but these models are being updated, in this case, 4 times. And definitely, I think we're seeing a more stable excess return throughout the years. So what you see here is the four folds. If you zoom in, this is the last fold. Okay, this is the third fold, etc. But it ends up being a seamless portfolio of 20 years because it's K-fold. If long short is what interests you, you can show the high minus low portfolio. You can disable the others, and that's a pretty good high low performance, always ahead of the benchmark. And finally, the other output that we have is your annualized returns by quantile, which you're used to from ranking systems. And again, here, overall, a 13% excess return versus the benchmark for an S&P 500 model. And there's definite consistency in the first and second half. First half, 13%. Second half, 12%. So again, these are things that we've never seen before. So yeah, that's so now you can decide which model is best for your features and your universe. And then you can decide to launch it to create an actual predictor that you can use in your screeners and rankings and whatnot. And you do that by doing this, create predictor. Of course, you have to train it because, are you going to use the entire 20 years? Maybe you just want to use the trailing 10 years. So you would do this. And then you switch over to predictors and you can train them. And once they're trained, they can start generating predictions. You can do predictions on this page just by going here, extra trees as of the latest data, predict. And these are the predictions. Again, they're normalized using z-score. So this 0.699 doesn't really mean anything other than it has the highest 3-month future performance prediction. To use them in your screens, simply copy the formula with this button here. Switch over to screens, new. It's right here. So paste it. Maybe do a variable so you can see it, prediction column. And here, if you don't have the stock universe as the same as the one that you used for your validation, you're going to get an error. Okay, AI factor so-and-so requires the universe to be S&P 500. So let's switch, run. Okay. All right, something is, okay, this was fixed before. Oh, sorry. I was in the wrong website. 1 second. Yes. Okay. I was in the development environment. Let me go back to the screens. Stock. Okay. Prediction. S&P 500. Okay, here we go. Yep. Sort by prediction. There you have it. So you can use this anywhere. You can even use it as a ranking factor. Yeah, just like any standard factor. So that concludes the demo. We have a lot of work ahead of us. There's a lot of work to do in feature engineering. There's not a lot right now, just basic statistics. Feature importance is coming soon, but the one that is model dependent. Other enhancements that we have planned is grid search. Yeah, you can see it here. Just a note on grid search, for example. There is a lot of power behind this system. And the idea is to let you do all sorts of data mining projects. For example, I did it here for the S&P 500. I did an XGB grid search that looks like this. Basically testing all sorts of combinations of hyperparameters. There is, I think, 300, more than 300. Yeah, oh, here it is. 216 different versions of XGB. And yeah, so there's a lot of power at your fingertips to do this type of data mining. So final thoughts. Yes, it is live now. During the beta period, maybe a month or two, there will be zero cost to you. And there's a new private forum in the forums that you can use to ask questions. And they will not be visible to non-beta users. So probably, so it's not confusing for other people. So please use the forum called, where is it? Yeah, AI factor beta discussions. It's locked, but you should have access to this. Okay. Yeah, that concludes the demo. So feel free to ask any questions. Let's see. Who, if you want to, oh, okay, James. Okay. That's James.
Yeah, thank you. My initial impression is that is absolutely awesome. I mean, it just is. I mean, I might have any little thing I say is just, I guess almost nitpicking. So I wonder, so you've got a lot of good people here. Is that the K-fold that we normally see, or is that more like a nested K-fold? And I don't know if I can instantly tell the difference, but I think someone like Pitmaster or some of the others can tell me. Because you have different updates along the way. Normally, when you do a K-fold, you kind of average all of them and find the one that has the best average, and you stick with it. But you're doing something a little different, it sounds like, and mostly that's probably a good thing. I'm not trying to be critical at all. That sounds more like what I would call a nested K-fold regression. And then one more thing about that, I would set a different gap between the front and the back. I think there's a big difference between the information leakage if you're training after the test period compared to before. And I think you'll actually get better K-fold results in there. And I think they're legitimate if you do that way. That's the two main questions.
Additional gap is certainly easy to do. And actually, I think it is in one of the tasks.
Okay.
The other thing is what we wanted to do. So maybe I'm not quite sure about the terminology, but we wanted to add some restrictions to K-fold so that we can create a portfolio. So by having this type of restrictions, we can then generate a portfolio, a continuous portfolio of 20 years. So I don't know if that answers your question, but
and actually that's probably a good thing because that does reduce what's called recency bias, which I think we encounter some. We see some of the designer models decaying, and it's because when they were created, they probably had a good recency bias, and they're not totally updated. But so here's my main question though: with a nested K-fold cross validation, you're going to actually have a different training sets for your final result.
1 second.
Different training hyperparameters for your final result. Whereas with a usual K-fold validation, usually they end up with the same hyperparameters throughout.
For now, we don't have a hyperparameter tuning built in. Something that it's coming with the grid search. So you will be able also to do a grid search of multiple combinations of hyperparameters to check out which one is the best. And yeah, it's actually thinking a little bit more about the context of nested cross-validation inside the grid search. It's something we'll definitely do.
Gotcha. So I was just a little confused on that. The way you're doing it is perfect. Got it. Thank you.
I see another question from Yuval. Yes, you can use a model you train on a specific universe on another universe. By default, we have a setting where we disabled that in order to avoid people potentially misusing the this feature. But yeah, if you select the right option, you can definitely backtest an AI factor with a different universe. A use case I usually do is I will test on a subset of the S&P 500, let's say random 250 stocks, and then I will do a backtest on the other part of the S&P 500.
Yeah, about that, the preprocessor, if you use Z-score, what is it going to do? It's going to calculate the mean and standard deviation of each feature. And it's going to remember that. Okay. When you do predictions, it's going to use that mean and that standard deviation to normalize the prediction data. So if you use Z-score, you probably shouldn't be switching universes. They're going to be complete.
Yeah.
So, you know, but if you're using rank, maybe it's okay. We're all learning, so we don't know what's going to happen.
I think that's a great point. Great point.
Can I ask a question?
Yeah.
Yeah. I don't understand the difference between training and predictor.
Well, training is maybe the wrong word, maybe validation and predictor.
But why do you have to do it after you've done all the training? Why do you have to make a predictor too? Can't you just use the model that you're just? I don't quite understand that whole thing.
There is 4 models here.
Okay.
Each fold is a model.
Oh.
There's a model created at the end of this green bar, which is used out of sample to create predictions here. Then it starts over. It trains another model here to generate these predictions. So all the models here use unseen data for predictions.
Mm-hmm.
All this work is so you can decide which model to use. That's it.
Oh.
Once you decided which hyperparameter, which model, and so forth, you then create a predictor, but a model doesn't do anything. It needs to be trained, and then you decide, okay, train it with, you know, how much ever data you want. You know, some people may want to create a predictor that only uses the most recent 10 years because they don't want to use really old data, right?
Right.
So nothing exists. This validation, all this work only generates results. There's nothing left here that you can use.
Oh, okay. I got it now. If you make a small change to the universe that you're using, then do you have to retrain your model? I mean, in order to use the factor, I mean, you have to retrain the factor in order to use it?
No, I mean, the factor will only complain if you have this setting on. If it's the same universe,
Mm-hmm.
you can change the rules.
Oh, okay.
That you're probably invalidating all your work, or maybe not. You know, who knows?
Mm-hmm.
Yeah, it doesn't, you know, and that's maybe something that we should consider in the future, locking down the components, because you're going to use the predictor. Now, if you start changing things like the universe and maybe the custom formulas that are being used, yeah, I mean, you can end up with something completely different.
Marco, I've actually tried that. So like for small caps, I train on the easy to train universe, but then I actually trade or even backtest on a slightly more liquid universe. But it benefits from the training on all of the stocks. And I think the backtest mainly benefits from just not buying illiquid stocks and paying all that slippage. But I do train on different universes than I actually use. And so you should probably keep it so you can, I think.
Okay.
Yeah, I mean, all you have to do is disable.
Perfect.
You know, where is it? No, I don't know where it is. Here.
Exactly. Yeah, but I wouldn't change that. So that's perfect. That's perfect.
And then when you're scaling the variables, Z-score is definitely inappropriate for certain variables. I mean, for example, market cap, you can't use Z-score for that. So can you specify different scaling for different variables? Can you use Z-score for some and rank for others? Or if I'm going to be using some variables that, you know, if you're using market cap alone, I mean, it doesn't make sense to do Z-score. So
I don't know if it makes. I don't know if it makes a hell of a lot of difference, but
oh, okay.
You know, again, we're learning along. But if you can certainly make market cap more.
Well, I guess my question is there an advantage to using Z-score over rank?
Yeah, Z-score keeps it like if you do rank, it's just an ordering, and it really messes up your regression if you have you know, like outliers and et cetera. It might be actually good to get rid of the outliers, but when you use the Z-score, it actually ends up being exactly like a real regression that's not converted to rank. So you can actually be doing a real regression with this. I don't know if I need to expand on that, but Z-score is totally different than rank. It's totally different.
So do all the different algorithms use regression, or some of them don't use regression, right? They just
correct.
Yeah. So for the
ones you're right, for a random forest.
Yeah. For random forest, I could use rank, right?
Correct. Absolutely.
There
but
is,
also even with rank, you want to know if it's normalized over just a day for your rank, or whether you want to normalize it over the whole training period. There's a big difference there.
Big difference. Yeah. Okay. Got it. Thanks.
Here's the market cap transformed with log, so looks a lot better. Will there be designer models that use AI factors? Yeah, that will be up to the designer models, the designers. Ricardo, any other questions? Great. So, yeah, I think play with it. Let us know. I think we can wrap it up.
Thank you, everyone.